So we were engaging ourselves with the module 5 of engineering physics. Yesterday we discussed about superconductors, and today we speak about photonics. What is photonics? Every electronics that is associated with light, photons, that can be called photonics. And photonics is of great importance today just because the photon-based communication is the rule of the day. And you know, all communication through the optical fibers are photon-based communication. And it's clear that today's World Wide Web, the internet, the backbone of the internet is optical fibers. And every communication, photon-based communication, is therefore getting great importance today. So before entering into the electronics aspect of this photon-based communication, we have to just understand the foundation principles of light generation and light absorption. This is given by other than Max Planck. Already in 1900, he produced a very interesting theory, which is the foundation theory of quantum mechanics. And that theory is known as quantum theory of radiation. And this is something which I have already seen in many ways. And this is represented by a very simple and cute equation. Delta E is equal to h nu. So this is the quantum theory of light. Due to Max Planck, delta E is equal to h nu. And in truth, this particular equation is a really wonderful equation, because you can say that the worlds are incorporated into this equation. What we see in the left-hand side of the equation, you can say this is the world of matter. What you see in the right-hand side of the equation, h nu, that's the world of radiation. So this equation basically means how the world of matter is related to the world of radiation. That is why it is called quantum theory of radiation. And what is quantized here? You can see there's a delta E in the left-hand side, which means that there are discretized energy levels, quantized energy levels inside the matter. And the quantization, I don't go to the details of the quantum theory as such, but according to quantum theory, when particles are confined, they'll be quantized. The energy levels will be not continuous, rather discretized, and the material will be quantized. So what we see inside the material, any material for that matter, will be large number of energy levels occupied by quantum mechanical particles. And what are quantum mechanical particles? They can be, for example, electrons, they can be nucleons, they can be atoms as such, or they could be even molecules. So you have the definition of matter, the left-hand side of the equation, which will be having at its heart many energy levels occupied by quantum mechanical particles. And on the right-hand side, you have the definition of the photon. The photon is defined by h is the Planck's number, and u is the frequency. So frequency is color, by the way. So a certain color of light will be coming out. So this is the basic idea. You can read this equation. Interesting part of this equation is that it can be read in both directions. If you read in the forward direction, the equation means that the light comes out of the heart of the matter. Light emanates from the heart of the matter. The different quantum mechanical particles, when they de-excite from a higher energy level to a lower energy level, with the difference in energy delta E, a particular quanta of light will be produced. So how light comes out of the matter? is what we, if you read in the right, from left to right, that is what we get. Now this equation can be also read from right to left. It means what will happen when light is falling on a material? A radiation is falling on a material. What will happen to it? You know, right now my shirt is looking blue. If I ask the reason why it is looking blue, I can say that I am standing in a background of artificial light here. Now it will be having a large number of colors represented by different hues. And out of all colors, material of my shirt absorbs all colors excepting blue. That is why the blue remains here, and that is why my shirt is looking blue. So, the phenomena of absorption of radiation by matter, that is what we get when we read this question from right to left. So, once again, how the light is produced, you can say this is what is called emission of photons. When we read this equation from left to right, now you can also read the equation from right to left, then it will be absorption. So, absorption and emission of a light is the foundational when we speak about photons. How photons are created, how photons are consumed or absorbed. So, this is the heart of the quantum theory of radiation. So, we can maybe represent it by energy levels. Let's say you have an energy level E0, a lower energy level, ground energy level, and let's imagine this energy level E1 is an excited level, a level higher than E0. Now let's imagine to this particular matter which is having these discretized energy levels by quantum mechanics, let's imagine a radiation is approaching, coming and falling on incident. And according to that particular theory, this light will be absorbed if this particular photon is having an energy which is equal to E1 minus E0. This is nothing but delta E. So the quantum mechanical particle which is sitting here, as I told you, this could be nucleons, electrons, atoms, and molecules. What will they do? They will absorb this light and will get excited to the higher energy level. So, absorption of light can be represented like this. Now let's also discuss about the emission of light. The emission of light happens due to a kind of de-excitation of the same particle from a higher energy level to a lower energy level. So what happens here is that a radiation will come out, which is having a definition h nu, which is equal to, again, E1 minus E0, or this is nothing but delta E. So, light will be absorbed, light will be produced, all according to quantum theory. Interestingly, the entire electromagnetic spectrum can be explained by this quantum theory of radiation by Max Planck. Let's imagine these quantum mechanical particles are nucleons. So they will get excited, the energy gap will be much larger, and these nucleons are excited, and you get the most energetic radiation, which is called gamma ray. So you can say that gamma ray is due to de-excitation of nucleons between nucleonic energy levels. Now what comes next in the electromagnetic spectrum? X-ray. So you can say that the inner electrons in the K shell, L shell, they are called inner electrons. They are de-excited from inner electronic higher energy level to inner electronic lower energy level. That will give you a highly energetic ray, which is less energetic than gamma ray, but high energetic ray, X-ray. X-ray is produced like that. So it's an electronic transition, but inner electronic transition. Inner electronic de-excitation gives you X-ray. Now, what comes next? Ultraviolet and visible light. Again, there is electronic de-excitation, but this time, these electrons are in the outer levels of outer shells of the electron orbits. For example, M-N shells, for example. Now, these electrons are de-exciting from outer shells. Then you have ultraviolet and visible light. Now, what comes next is infrared. You know, you have to imagine right now atoms and molecules as the quantum mechanical particles. And we are excited somehow to the higher energy level. And in this case, it's a vibrational energy level. Atoms and molecules are vibrating. And these vibrational energy levels are created, and a higher vibration energy level, these atoms, molecules are de-excited to a lower vibration energy level. This will give you, again, another light, another photon, which you call infrared. Now, the next question is, what comes next in the electromagnetic spectrum? Microwave. The microwaves are, again, due to atoms and molecules, but this time, there's a rotation for these atoms and molecules. So the transition of a higher rotation level to the lower rotation level by atoms and molecules, they will give you the microwave. And what comes next? Microwave. Now you can say that these microwaves are due to spin reversals. Atoms, molecules, all quantum mechanical particles, most of them are having spins, up spin, down spin. Up spin is having higher energy, and down spin is having lower energy. So a transition between up spin to lower spin, up spin to down spin, that will give you another photon, which you can call microwave. So the entire electromagnetic spectrum can be explained based on this quantum theory of radiation. Now, we have studied what is quantum theory of light, how to create photons, how to absorb photons, but you have to relate that with the electronics. You know, the foundational component of electronics is nothing but p-n junctions. So let's analyze how p-n junctions are absorbing and emitting radiation. So before going to that, we should know what is a p-n junction. We have studied many things about it, but at the same time, right now we have to summarize and understand in a clear sense. You know, we have, for example, we have an intrinsic material. Intrinsic material which is used to develop P material or N material are generally tetravalent materials. The elements which falls in the group 4 of the periodic table, which means they are having 4 electrons on the outer shell. Now, this particular material, for examples are carbon or silicon, germanium, etc. So these materials are used to create p-n junctions. First, let us think how we can make a p material. You know, we take this intrinsic material. So, you know, the intrinsic material will be having, as I told you, tetravalent materials, and they naturally absorb either light, as we already saw in the quantum theory of radiation, or they can absorb heat energy and get excited. Get excited means there will be charges created, electrons and holes. And therefore, we can imagine that there are some intrinsic electrons and holes here. Now, to that intrinsic material, which is already excited and having some charge carriers in a balanced way, electrons or holes in equal number, we are doping. Now, first we discuss about p doping. What is p doping? This intrinsic material is doped by trivalent materials. You have seen that. So, you know, there will be a total number of electrons at the outer shell will be 7, which is 8 minus 1. And you know, all atoms will try to have octaves in the outer shell. That's a perfect number. But right now we have only 7, 4 plus 3. And therefore, there will be absence or vacancies or holes for electrons. Absence of electrons, absence of negative charges will be there. absence of negative charge you can represent as a positive charge. So there will be positively charged holes in this particular material when an intrinsic material is doped by a trivalent material. And as I've already told you, there will be also some amount of electrons here because of the intrinsic excitation, thermionic excitation or photo excitation of the intrinsic material will give rise to holes and electrons already. So some amount of electrons will be there as their minority. The majority will be then holes. So therefore we have a definition of a p material. P material is a material with majority carriers as holes and minority carriers as electrons. Now we can also create a n material in an opposite way. In this case, this intrinsic material, which is already excited and having some charge carriers, are doped with pentavalent elements, materials. So penta means 5, so you can have 4 already there on the outer shell, 4 plus 5, 9, so 8 plus 1. So one extra electron will be there. So there will be large number of electrons in this particular material, which we call n material. And as I've told you, by the excitation of the intrinsic material, you will be also having some holes. So we have the definition of p material, n material. What is p material? P material is a material with majority carriers as holes and minority carriers as electrons. And n material is a material with majority carriers as electrons, minority carriers as holes. We have already said 3 things are happening. Now let's consider the energy level diagram for this p-n junction. And this is very important because you know, according to Planck's quantum theory of radiation, energy levels are creating photons. Delta E is equal to h nu. So when we think about the absorption or emission of light by a p-n junction, you have to consider the energy level diagram for this. And you know, there are 2 important energy levels. You call it the higher energy level, we call it conduction band, and lower energy level we call valence band. Conduction band will be containing electrons. Electrons will be occupying the conduction band, and the valence band will be containing holes. So we have p region and n region with the conduction band and valence band. Or everywhere the higher energy level is conduction band and lower energy level valence band. And you can also think about a Fermi level, a level which is called Fermi level, which is a level till which this particular levels are occupied at absolute zero of temperature, which means without any thermal assistance. 0 Kelvin means there is no thermal energy, so thermal energy is not supporting this filling. How much of the valence band will be filled? I have told you, valence band will be filled with holes and conduction band will be filled with electrons. And the level of filling at absolute zero temperature is what is called the Fermi energy level. F stands for Fermi, Fermi level. So it is the highest filled level for both for holes and for electrons. Holes filling valence band and electrons filling conduction band. There's yet another thing you should remember. That is the gap between the conduction band and valence band. This is what is called the energy gap. And this is the delta E, which we have to consider for the absorption and emission of light. And there again, you find another potential, which will be, which I have already told earlier, a barrier, energy barrier, a potential barrier, which is created. Now, energy gap is fixed when we fix the material, but the barrier, potential barrier, is not fixed. It is depending on the biasing. So this is function of biasing. So this will be keep on varying. Biasing means an external potential given to this particular PN junction. If you are not giving no biasing, either forward biasing or reverse biasing, we'll discuss about that later. If you are not giving any external bias, then it will be some value. But provided, depending on the nature and the value of the external bias, this potential barrier will be moving and changing. So this is the foundational thing happening in a PN junction. Once again, the energy level diagram we have to take care. There's a conduction band and valence band both in P and N region. And there's a depletion region also in between. And every important phenomena related to absorption and emission of photons will happen in the depletion layer of the PN junction. So we have already seen the formation of a PN junction. And right now, we are going to analyze what will happen if you are forward biasing a PN junction. By forward biasing, you know what is meant by that. You connect this PN junction with a battery with its positive potential connected to the P region, as I have shown here, and negative potential of the battery is connected to the N region. So you should appreciate that there are two batteries right now. One is the interior battery, which is very much there for the PN junction, internal bias. Now we are giving an external bias, a bias from outside. So internal bias and external bias. Let's see the functions of both bias. How does internal bias work? You know, internal bias is negative here and positive here. And now you can easily imagine it will work on the minority carriers. For example, in the N region, you have minority carrier as a whole, which is positively charged. Now, these positively charged holes will be drifted towards this negative potential, internal negative bias. So we should also understand what is meant by drift. You have already seen another concept, diffusion, which is purely dependent on the concentration gradients. Now, the drift is something which is depending on not on the concentration gradient, rather electric potential, electric gradient, or electric field. Now, we know there is an internal electrical potential, internal electrical barrier, or internal electrical field gradient, any name you call, which will act upon the holes, which will drift these holes towards this depletion layer. And similarly, the minority carriers here in the P region, which are electrons, which will be internally drifted towards this the positive side of this internal bias. This will be happening all the time. And there will be a balance. If there's no external bias, they'll be reaching a balance, and the net current will be all zero. Because so much flow here will be balanced by the flow of electrons, and it will be all balanced. But when you give an external bias, this balance is broken. You're giving a very high positive potential. Of course, the internal potential in this side is negative, and very high negative potential to N region, where you have a positive potential. Now, how does this external bias work on the system? That is the question. External bias is preferentially acting on the majority carriers. For example, the majority carriers in the P side are holes, and it is getting a positive potential. What will it do? These holes will be drifted towards this. Holes will be drifted. Holes will be drifted in the opposite direction. So major flow of holes will be happening here under forward bias. I show these thick lines to show the major flow. And similarly, a major flow of electrons which will happen, which will be drifted by the negative potential from N side to this depletion layer. So, in the depletion layer, moreover the drift which is given by the internal bias, a major drift of the majority carriers are happening when we are forward biasing. And what happens there is large number of holes will be coming from P region to depletion layer, large number of electrons will be coming from N region to depletion layer. This is not a diffusion, this is a drift under the electric field, under the external electric field. Now, the conduction band of the N region will be depleted and the electrons will be coming to the depletion layer, and which will fill the depletion the conduction band of the depletion layer. Similarly, holes will be coming to the valence band of the depletion layer and be filling the valence band of the depletion layer. And now something very important happens. There will be a process which is called recombination of electrons in the conduction band of the depletion layer with the holes in the valence band of the depletion layer. Once again, there will be a recombination. As you know, electrons are always looking for recombining with the holes. The holes are there in the valence band of the depletion layer and large number of electrons in the conduction band of the depletion layer. And then happens this recombination. The electrons in the conduction band of the depletion layer will be recombining with the holes in the valence band of the depletion layer. And you know, as a result, there is a de-excitation happening right now. You can imagine there's a de-excitation. That's why I've shown this with the downward arrows. De-excitation is happening, and you can imagine then a light will be coming out. The light will be coming out, which will be depending on the energy gap. Not on the internal potential barriers, but right on the energy gap. Now, if it is around 1.47 or so electron volt, the corresponding light will be red light. So, red LED you will get. So, this is what is called LED, light emitting diode. So, you have a diode here, a PN junction diode, and now you are giving a forward bias to that PN junction diode, and a forward biasing of PN junction diode will lead to the recombination of electrons in the depletion layer with the holes in the valence band of the depletion layer, leading to the production of or emission of the radiation, which is having a frequency corresponding to the energy gap of this particular PN junction material. So, depending on this material, you will have the light. So, that's the important thing. So, you have to choose materials appropriately to have different values for EG, energy gap, the gap between conduction band and valence band, and that will be determining the color of the light. Color, as I told you, is the frequency. The frequency will be determined by the energy gap. So, you can think about LEDs of different colors as we have seen in our life, and this is possible by choosing different material, different energy gaps. So, this is the effect of forward biasing. When you forward bias a PN junction, you get emission of light out of it. So, to get light out of a PN junction, to produce light by using a PN junction, you need to forward bias the PN junction. Now, let us discuss what is happening under reverse bias. Under reverse bias, you already know the external bias, the negative potential of this external bias is given to the P side, and the positive potential is given to the N side, which means you can imagine externally looking electrons will be attracted to this positive potential, holes will be attracted towards this negative potential. But at the same time, you can imagine there will be drift of the minority carriers in the P side, and there is also drift of the minority carriers which are holes in the N side, And that drift of the minority carriers are promoted. Holes are moving in this anti-clockwise direction, and electrons are moving in the clockwise direction. Which means, in other words, this particular barrier will be expanding itself. And this will be reflected in the energy level diagram. The highest filled energy level, which we call Fermi level in the P region, EFP, is lifted up. And similarly, the Fermi level in the N region is lifted down, making the barrier very steep. For electrons, this is the barrier. It has to climb this barrier. For holes, even though it looks down, it goes down, it's like a slope. If it were electrons, it were a slope. But for holes, it's a hill again. You have to see it's in a reverse way, because it's positively charged. So for them, the hill is also, for both of them, both charge carriers, the hills are becoming steeper and steeper as you increase the reverse bias. Or in other words, the barrier is expanding itself, and therefore it is very difficult for electron and holes, electrons from the N region to reach the P region, or from electron from P region to go to the N region. So basically there will be only minority currents present here, current due to the minority carriers, which is already there. So therefore, you can say that this particular p-n junction will be becoming non-conducting. It will not be allowing diffusion, it will be not allowing drift, it will be expanding this barrier, and therefore a p-n junction which is under reverse bias condition will be absolutely non-conducting. So in other words, a p-n junction will be like a valve. It will be conducting under the forward biasing condition and will not be conducting, will be closed in the reverse bias condition. So it's like a valve which is open in only one direction, and that direction is the forward biased direction. It will not conduct in the opposite direction. So it's just like a valve. So that is the use of this particular p-n junction. In any circuit, it operates like a valve. Now let's imagine, towards this particular p-n junction, which is under reverse bias, let's throw light to see whether light will be absorbed by this. And you know, the absorption of light by any material is discussed under photoelectric effect. This is the masterpiece of none other than Albert Einstein, who made this theory of photoelectric effect as a part of his doctoral thesis. Already in 1905, he has created it, for which he got Nobel Prize. So it's a Nobel Prize winning idea, the photoelectric effect, which is, the idea is created by none other than Albert Einstein himself. He didn't get Nobel Prize, for example, for his theory of relativity, but for photoelectric effect, he got Nobel Prize. As the very word means, it's a photoelectric effect. Photo means photons, electric means electron or holes in this case, because there are two charge carriers for the p-n junctions, they are electrons and holes. Now the question is, what will happen when light is falling on this depletion layer which is under reverse bias? There will be photogeneration. That's the first point we should see. There will be photogeneration of charge carriers. There will be, due to photoelectric effect, there will be photogeneration of charge carriers. Charge carriers, as you know, are electrons and holes for p-n junction. So what actually happens is that a photon falls and kicks off electrons from the hole. So electron will be freed and holes will be also freed. So there will be large number of electrons and holes created here. So let's say electrons are created, large number of electrons according to the intensity of the light. In the depletion layer, they are created. Large number of holes. Actually, they are created together. Electron hole pairs are created. This generation of electron hole pair, but you know, there's a bias here. Because of the bias, the generated electron hole pair will be separated. So this is, it will be separated. Attracted electrons will be attracted towards the positive potential. Both intrinsic bias and the external bias will be all driving the electrons in the clockwise direction. And negative potential, intrinsic bias and extrinsic bias, both of them will be driving the holes, the anti-clockwise direction. So the circuit will be completed, and large amount of current will be flowing through this particular circuit. This is what is called photocurrent. So in other words, this particular PN junction can be also used to detect photons. When photons are falling on the depletion layer of this particular PN junction under reverse bias, we can detect photons as electrons and holes. Electron and hole current, the current will be created, electrical current will be created when photons are falling. And the intensity of the current will be proportional to the intensity of the light radiation. So not only the presence of the photons can be detected, but the intensity of the photon which is falling on the depletion layer can be determined by measuring the current which is flowing through the circuit. This is amazing because, you know, when we use this kind of devices in a photonic environment for production and detection of light, in the photon-based communication. In a photon-based communication, you can imagine there are three steps. The first step, there is a transmitter, which will be basically the photons. So the LED, which is forward bias, can be used as a transmitter, which can create, for example, we have already seen LED, the light emitting diode, which creates light. That can be used in the transmitter side. And of course, there will be a channel. We'll be discussing about the channel. They are called optical fibers, which we'll be discussing tomorrow. Now, on the receiver side, you need to have some kind of this reverse bias PN junction, which can be then called a photodiode. So photodiode is nothing but a PN junction with reverse bias. It's a photodetector. It detects the photons, and it also allows you to measure the intensity of the light falling. So it detects light and measures the intensity of light. So therefore, if you can send a signal by transforming the signal into a photon and carry that photon through an optical fiber, and the other end, you can detect the photon using a photodiode or a photodetector, measure intensity, and recreate the signal, then the communication cycle is complete. So a transmitter with LED and a channel using optical fiber. On the other side, you have a photodiode as a detector. So you have a transmitter, the channel, and receiver. So this completes the cycle of communication based on photon. Now, we should also see that these photodiodes, this particular depletion layer is already expanded a little bit due to the reverse bias, but this may not be sufficient. You need to broaden this area as far as possible, because light is supposed to fall on this depletion layer. If it falls anywhere else, it does not create this effect. Therefore, you can think about adding a region which, using an intrinsic material, which I already seen in the first part of this lecture. Intrinsic material is sandwiched in the middle of the depletion layer, so that you are expanding this particular depletion layer where you expect the light to fall, which has to be detected and detected or measured, whose intensity has to be measured. So this is what is called then a PN junction with the intrinsic material in between. So you have not a photodiode, rather this is called pin photodiode. And I stands for the sandwiched intrinsic region between the p-n junction. So pin photodiode is supposed to work better than a p-n junction photodiode, because you have expanded the middle region, which will be able to receive large amount of light in a better way, to produce large amount of currents, corresponding current, and it will be then more sensitive to operate. Now, let us discuss solar cells. Solar cells are very important power generating system in the modern world. And we are very proud as Kochais, people live in Kochi, that our international airport is fully energized by photovoltaic cells. And you generally call them solar cell. So let's think about the working of solar cell. The solar cell is again a p-n junction with all the discussions holds. Majority carriers, the p side holds, electrons minority carriers, n side electrons majority carriers, holds minority carriers. And due to the internal bias, there's a slight drift of the minority carriers. It's a current which it creates, which balances itself. These currents will be all balanced. J is equal to 0 when there is no light falling. Now there is no external bias. We just put a galvanometer to measure the current, to see the current coming, and a meter to measure the current. So that's all the system which we have. Now let's imagine to this particular deposition layer, where you have, as I told you earlier, there is a insulating region, there's a small battery, internal bias, and there is also a potential barrier. We don't consider that as important in this particular case. Now let us see what will happen when light falls on this particular material. We have seen the photoelectric effect. When photons are falling, the photoelectric theory by Einstein, it says that these photons, each photon will kick out the electrons from electron-hole combine, which means electrons will be out and holes will be also separated. So electrons will be out, holes will be here, this is broken, and electrons will be out and holes are broken. So you have, by 3 photons, 3 electrons and 3 holes generated by photons. So this is what is called photon-generated charge carriers. So the basic effect of this photon falling on electron-hole combine is that the charges will be separated, charge separation. Now charges are separated by these photons, but now the question is, how can it drive? You need a potential difference to drive this current. And I have told you, we have a small battery here, internal bias. We don't give any external bias to the solar cell, but it is having an internal bias. So which will cause the separation of these charges and flow of these charges through this circuit. There are 2 charges, electrons. So electrons will be moving in this direction. The photo-generated electrons will be moving in this direction because of this positive potential. And photon-generated holes will be moving in this direction. So this is a similar direction of the minority carriers movement, which is drifted by this potential. So in other words, the holes will be moving in the anti-clockwise direction, and electrons will be moving in the clockwise direction through the circuit, which will be making a current. And that current can be connected to any load to do its job. So this will be creating real electrical power, which can be used for different purposes. I told you, Our Cochin International Airport is proud to be fully driven. All equipments are driven by the photoelectric cells, photovoltaic cells, which are in general called solar cells. Now let's imagine the practical making of this particular solar cell. We are doing an experiment in the lab, by the way, on solar cell, and we have already said that, the N region is taken at the top and P region at the bottom, because we said, electrons are 3 times mobile than holes. Holes are a little sluggish in movement. Electrons will move 3 times faster. So therefore, if you want to get a good current here, we need to optimize the thickness of the N region and P region. P region should be 3 times larger than the N region, so that the time taken for holes to travel from the depletion layer, as I told you, it is at the depletion layer, the charge suppression is happening. That time taken should be equal to the time taken by the electrons to travel from this depletion layer to the next electrode. So therefore, only then the circuit will be perfectly complete and the current will flow. So construction of a PN junction, which is operating as a solar cell, you have to have N at the top and P in the bottom. And N should be 3 times less thicker than the P region to satisfy this condition. And it also facilitates the light to fall on the depletion layer. Because if this is very thick, light will not penetrate and reach this particular depletion layer. And this has to be transparent also a little bit, or at least translucent, so that light should be reaching this depletion layer. So this gives you the practical idea of design of a solar cell. So once again, solar cell in actual practice is designed in such a way that N at the top and P at the bottom, and P having 3 times thickness as the N, and N made of the translucent or transparent material, so, all in order to facilitate light to fall the depletion layer, where this particular process of photogeneration and suppression of charge carriers is taking place. Now let me conclude this particular session by speaking about semiconductor lasers. Even though it is not part of your regular syllabus, we are using a good number of semiconductor lasers in the lab. So in order to understand how they are operating, how they are working, maybe it is good for us to know how the semiconductor lasers are made. The major difference in the making of a semiconductor laser is that it is not just a PN junction. Rather, it is a P plus N plus junction. By that we mean the P material is a material which is heavily doped. And similarly, N material heavily, which means that there is a heavily doped P material joined together with heavily doped N material. And this will be reflected in the Fermi level diagram. The doping should be such an extent that a Fermi level drone will be lying in the valence band of the P plus region, and which will be at the same time lying in the conduction band of the N plus region. This is what is called doping till degeneracy. So such an amount of doping should be there for this material to be operating as a laser. And I hope you know the difference between an LED and laser. LED is producing light, of course, when a PN junction is forward biased. It's a just PN junction, not P plus N plus junction. PN junction forward biased gives you LED. And what happens there in the production of light can be described as a spontaneous emission of photons. So electrons and holes are recombined, as I told you in the earlier session, and spontaneously, at the same time, simultaneously, they are creating this particular light, which is called LED light. And the difference from LED to laser is that laser is due to, as you know, it is light amplification due to stimulated emission of radiation. Stimulated emission. SE stands for stimulated emission. So therefore, we have to create a condition for stimulated emission. I have already told you the material condition, the level of doping the material should be having. This P and N material should be doped in such a way that the Fermi level lies at the same time in the valence band of the P plus region and the conduction band of the N plus region, which means this is doped till degeneracy. Such a material is given a forward bias. Now, on the forward bias, there is also another condition. Let's imagine we are forward biasing. We are drawing a curve between the forward biasing current and the power of the light which is coming out. Just imagine that we are giving a forward biasing till this particular point, which is corresponding to a critical current, because a critical phenomenon is going to happen beyond this forward biasing current. That is why it is called a critical current. Now, this particular region, as you increase the forward biasing current, the brilliance of this LED will be linearly increasing. The power or intensity of light output will be linearly increasing till this particular critical forward biasing current. Now, if you increase a forward biasing greater than IC for a P plus N plus junction, what happens is very dramatic. This linear power increase will be switching over to a exponential power increase. The brilliance will be exponentially improving and increasing. That is when we say this particular light is not due to spontaneous emission as in LED, rather it is laser. So you can have two regimes for this particular PN junction, even when it is P plus N plus junction, depending on forward biasing. Forward biasing current below IC will give you LED, which is due to spontaneous emission of photons. Whereas, if the forward biasing current is greater than IC, then you have stimulated emission of radiation. You have laser. So here you have light emitting diode, and here you have, in this regime where forward biasing current is greater than a critical value, you have semiconductor laser, which, as you know, is a very powerful and coherent light source. Both spatially and temporally, they are coherent. That is why when you switch on a laser, it travels in one direction. It's a directional light. It is spatially coherent light. And again, it's highly monochromatic. It's very brilliant red color, which I've seen in the lab. LED is not that brilliant. So brilliance means monochromatic. Or that particular light is very highly monochromatic. So you have a highly monochromatic, highly temporally coherent, and highly directional, highly spatially coherent light, which we call semiconductor laser. So we have discussed two things right now, two types of emission of light. One is emission, spontaneous emission from LED, and second, stimulated emission in the laser. And what happens, for every laser, there's a condition of population inversion. Should happen. So that can be explained like this. In the depletion layer, the conduction band of the depletion layer will be highly populated by electrons, and the valence band of the depletion layer will be highly populated with holes. So this is what is called a population inversion in the case of a semiconductor laser. Now, to this population inverted material, if you send a trigger, what will happen? All these electrons in the conduction band of the depletion layer, we will be simultaneously recombining with the holes in the valence band of the depletion layer, which give you a flood of powerful light due to stimulated emission, and that is which we call semiconductor laser light. So to summarize the session on photonics, let us go like this. As I told you in the very beginning, this photonics is very much related to the communication today. As I told you, the World Wide Web or the internet is almost completely, or 90%, is made out of this particular system. You know, for every communication system, you know, there's a transmitter and a receiver. And the transmitter and receiver will be connected by a channel. So in the optical communication or photonics, we have transmitter. So any kind of signal will be converted into photons, either by LED or by laser. So this conversion of signals to light, that is what is happening in the transmitter. And that light, when it's produced, let it be LED or laser, spontaneous emission or stimulated emission, it will be channeled through the optical fiber. So optical fiber can carry these optical signals for long distances. And about this optical fiber, we discuss tomorrow. Now on the receiver side, you know, these signals which is carried by the optical fiber has to be decoded. So basically, this is sensed by, we have discussed photodetectors, we have spoken about PN photodiode, which is sensitive, but sensitivity can be improved by introducing intrinsic material between, so you have PIN photodiode. So this is a short story about the optical fiber communication. A transmitter operating on LEDs and laser, which is basically a PN junction in the forward bias condition. And on the receiver side, a photodetector, which is either PN photodiode or PIN photodiode, which is again a PN junction, but in the reverse biased condition. And we have also discussed about the solar cell. This is not biased externally. You know, but for all PN junctions you have seen, there is an internal bias. So here we are speaking about forward external bias, and here we are speaking about reverse external bias. So once again, the transmitter side will be constructed by a semiconductor PN junction, which is forward biased externally. The receiver side will be equipped with another PN junction, which is externally or reverse biased, acting as a detector of this particular signal. This is how the total photonics works, and tomorrow we'll be coming back to discuss about optical fibers. Thank you.